Okay, so today I want to continue talking about network architecture search. The idea being that we try to find better architectures for our deep learning pipelines for a particular task, and in particular also for particular hardware, like a small microcontroller, a mobile phone, a desktop PC with a GPU, and a data center all have very different computing resources and very different bottlenecks. So if you want to have best performance on a microcontroller, then your architecture will look very different from the best performance in a desktop and a GPU scenario. Also, there's two parts usually to the performance of a network that we need to keep in mind. One would be the throughput, so how many images per second we can process. And the other one would be latency, right? Because how long does it take before we get the result for the image that we're currently looking at? If you're trying to do soccer playing robot, you need to react to the ball very quickly. If it takes you 1 second to detect the ball, then it's already too late. By the time you go there, do something, the ball will have already been kicked somewhere else or rolled further. So we need to worry both about the throughput as well as the bandwidth as well as the latency. So now, last time I actually started with I want to do a little sample problem that we can look at for trying to do network architecture search. So I wanted to create some random sample images and then have a red rectangle size 3 to 7 in there, and then train it 0 if there's no red square, 1 if there's a red square in the image. But that turned out not to be too easy, or as easy as I had hoped with my particular architecture. And I don't really want to make the architecture any larger, because otherwise the training would be would take too long. So I think I'm going to simplify the problem. So instead of having all these rectangles, we just pick one background color and then either have a red or a white square. Red or some other square. So we just do it on black, and then all we need to detect is basically if it's a red square or not, and then see how fast that will train. Yeah? Yeah, I think I did. So now here I'll change the create image function. Size 16 by 16 and no background images, and the target color red. Yep. Or we just take a so let's take a background color that is different from our target color. Then we don't want to add the colors. And then with 50% probability, we create a square, and with otherwise we create a red rectangle in a random position, and then we see if we can train that. And I'm just going to comment this out. We'll add the background color later. So here we create a rectangle. We set it to the target color and is square. Okay, let's try that. Create some sample images. Hey? Oh, no background squares. So here's a square, here's a rectangle, this is a square, square, rectangle, rectangle. see. You can try your own network architecture. Here I just generated a simple one using convolution, null networks. And we use the binary crest entropy problem, criteria loss function, which is 0 and 1 output basically of that one neuron. I don't want to run at 100. Let's just take 10 epochs. And let's just try them first. On the same data set. Now we have 60%. %, is if we throw a coin, so that is not actually doing any learning. So let's have a look at the output. So it does generate different outputs. So let's print out the loss function as well. And that would be and then we're going to return the average loss here. Here, we just evaluate the number of correct ones. So train, this would be average loss. Loss. And we want to not print the output that it learned. So here the loss is slowly going down, so that means we can run more episodes, and let's see how much we can speed it up if we put it on CUDA. Now to let it train faster, I think I can use a higher learning rate. Maybe .9. So the loss goes down, but our actual accuracy hasn't improved yet because hasn't switched the thing yet. So maybe we need to run it some more. So I want to try and move it onto the network. Let's see what Google allows me to do. Version 5 E1 TPU. So let's see. We need to go and go. How come? docutil. Let's see what we have now. Okay. So then we have this. Okay, never mind. Import torch. Oh, no CUDA. Okay, so I guess that only works for TensorFlow then. Okay, but since I wrote it already in Torch, I guess we're just going to write the next one in TensorFlow. Okay, now it learned it correctly. So this is an easier problem now than having the random background rectangles. Now, of course, I could just stop it here. Don't need to go. So let's say 200. And now we also have 100% accuracy for those. But right now I only used a data set for training. Now I'm going to use a different one for evaluation. And since it's such a synthetic problem, I can actually generate new training sets all the time. So we'll see. Now it gets worse. There we probably need to run it some more, and also let's take some more images. I'll just let that finish. And then in the meantime, while this is running, our focus is really not on this particular problem. Rather, to look at the problem of finding a optimized network architecture. So if we look at the architecture that I have so far, then I just started with a guess because I just copied the architecture before I even thought about the exact problem that we're trying to solve. So the architecture was this one here. Which is just a fairly traditional version of a convolutional network, right? Several convolutional layers, pool, followed by a convolutional layer. If I wanted to, we would also add a dropout layer. We could do that to force the neurons to actually specialize. So I haven't done that in this particular system, but that's certainly something that you would find in a convolutional network like this quite often. So now the question is this a good architecture or not? If we look at our training results, then it does learn, but it's certainly not an easy task. Even though you would think that this is a very simple problem to detect a red square from a red rectangle. Actually, I have a small bug in here, I think. What was the bug? Oh. When I create the image, yes, I think I may have made a mistake and added some of them that are actually square. That I need to fix. then it's always a square. And yeah. Um, yeah. Okay, then what kind of architecture would you um, propose in order to improve either the accuracy of our network or the computational cost? Maintaining the same performance, at least, while reducing the number of operations that we need to do, improving the bandwidth and reducing the latency of our model. So if you want to answer that question, then we can look at search. In this case, specifically searching for a suitable or an improving but at the heart, we have a search problem here, which is not unusual in AI applications and prompts, right? We always have to deal with some kind of search. Often we have to deal with some kind of search. So in this case, what can we do? Like if you start with our current architecture, then how would a search progress? Well, you can look at the architecture that we have here, and then you can kind of do your search process. How would you do that? How would you try and improve this? For whatever metric, accuracy, throughput, or latency. Well, one thing you could do or should do would be to kind of come up with an idea of what alternatives there are, right? So in a search process, one crucial One crucial concept is the idea of a hypothesis space, right? So that's kind of all the possible things you can do. And search for network architecture is not really that much different from search in trying to find a solution to some kind of logic puzzle, or find a solution to Towers of Hanoi, or find a solution for how to win in solitaire, or with a small variation, two-player games like chess or something like that, right? If you think about trying to find a strategy for winning at chess, then your hypothesis space would be the legal moves that you're allowed to make, right? For some concept of winning, you can also play chess, pull out a gun, and just shoot your opponent, which probably means that you also win the game, but it's not what you would usually, what should be included in your hypothesis space, that kind of violence, or start a fist fight or something like that, right? Or toss the board. Sometimes children do that. So the hypothesis space for network architecture would be the possible network models that can solve the problem accurately and efficiently. So in our search process, this page is huge, right? All the possible ways that we can construct networks would be just for standard, if we only consider one type of neuron, which would be, let's say, rectifying linear units, then you have to determine the number of layers that you have, and the number of neurons per layers, and then the number of weights per neuron, right? So that would be a huge search space. So let's say we have a network with two inputs. And two layers of rectifying linear units. And one output, then the total number of possible networks that we can build and we want to mask out some connections between the neurons. Then assume that I have N1 neurons in the first layer. and N2 in the second hidden layer. Then I have two input neurons. Now each one of the input neurons can be connected or not connected to one node in the first hidden layer, right? So how many different networks is that? Well, each from one input node, I can connect to any one of the nodes in the first hidden layer. So I have N1 possibilities there. Each one of those can be turned on or turned off. So that would be 2 times 2 to the power N1 plus then I have N1 neurons in hidden layer 1 and I have N2 neurons in hidden layer 2. They can be connected. So that would be N1 multiplied by N2, 2 to the power of N2 plus N2, and then it goes to a hidden layer. So that would be just 2. I have N2 layers and they go to 1. They may or may not go times 1. So this grows exponentially in the number of neurons that I have in the individual hidden layers. So this is exponential in the width of the layers. Right? So this is an extremely large search space. So now for the search, it's impossible to enumerate so we have to sample that search space somehow. Make a random selection or something a bit smarter maybe, but we need to be able to generate possible candidate quickly. So one popular strategy then would be to make modifications to an existing solution. So instead of having this enormous space and then just picking some at random, I may have a solution like we have now, right? We have one network that can learn this function. Then we can try and find a better one, making improvements to the architecture that we have. That means we only need to look in the neighborhood around our current solution. So that's what this defines a search strategy. A method for sampling this hypothesis space. And just to repeat, our search space most generally would be all possible kind of neural networks that we can generate, but because of this enormous size, often we're limiting it to, let's say, varying the depth of the layers, or which means the number of stages that we can have, or limiting it to the width, changing the width of the various layers. That greatly reduces the types of networks that we can generate. So this method for sampling the hypothesis space, there's different variations. One would be random search, right? Which would be, you just pick one of the candidates at random from the search space. Otherwise, you can, you also have grid search, which is kind of popular, where if you set bounds, so a one neuron hidden layer is not going to be very useful usually, right? Unless it's the output. 1 million layer is also not going to be useful, most likely. A layer with 1 million nodes. So you say, okay, in the hidden layer, I consider 4, 8, 16, 32, and 64 nodes, and that's it. Not any more than that, right? But then you already constrain the set of possible neurons. Or you can say, I just changed that in my search strategy, and I start with 4, 8, 16, 32, and 64 neuron wide layers. And then if the result is good, I make it smaller. If the result is bad, I increase it, for example. That would be a search strategy. Another kind of search algorithm that is very popular in this kind of scenario is usually genetic search, genetic algorithms. Where the idea is that you take network architectures, and if you have two good candidates, you try and merge them somehow. Kind of like evolution. Otherwise, you may define an error function, and then you can run gradient descent, or reinforcement learning can also be used. Now, in order to guide our search, we need to have a way that we can evaluate different candidates, right? Otherwise, I can pick this network, I can pick this network, but somehow I need to be able to say which one of those is better. Just like if you want to play chess, you need to figure out which move is better than, is this move better than this move, right? So we need to have some kind of accuracy measurement or performance estimate. And this is basically true for all search algorithms. You always need to have these three things at least. And what you do is your search strategy picks a candidate, you evaluate the candidate, then you feed that back into your search strategy to pick a new candidate, hopefully a better one that you already have, or some kind of guided search rather than just blind random search, hoping for the best. Now, for the performance evaluation, in networks, that's pretty difficult. Because the most intuitive approach would be to train from scratch, right? You create a network architecture, you use your training data to train it, then you evaluate how well it works. But, so we'll call that training from scratch. But this is very time consuming, right? This is very slow. So we'll look at some improvements, in particular with respect to neural network search, neural network architecture search, that hopefully allow us to do this accuracy estimation more efficiently. Because if you look at it here, I don't know if it let me, here with our network, took 5 minutes to train, and this is a very simple problem. So if we have billions of candidates that we need to evaluate, and every evaluation takes 5 minutes, then it's not going to be very likely that we're going to be able to finish this in a reasonable amount of time. So this is one thing that's specific to search for network architectures. Other thing like solving the towers of Hanoi problem, at least you can check very easily whether you got closer to the goal or not. You can check that in nanoseconds, because you just need to check if you're in the goal or how far away you think you are from the goal. So that can be evaluated extremely quickly. That means we can put more effort into our search strategy, because we don't spend that much time. With network search, once we actually create a candidate, to evaluate that candidate is time consuming. Which of course, that kind of trade-off or change will definitely impact the way that you can search the space. So even with a large data center, if you were to do that on something like YOLO or the VGG, the ImageNet data set, that's millions of images. To train the network on millions of images is going to take a lot of time, no matter what you do, right? So then it will take way longer than 5 minutes to train a candidate. So you cannot evaluate too many candidates if this is your training cost. So it would take like hundreds of thousands of hours on a GPU to calculate that. So one possibility would be, and the other thing is that as if you have one network architecture, right? if it takes you several hours to train a network, you won't be able to evaluate many architectures. You won't really be able to search for a better version. But using this idea of inheriting weights and the hypernetworks, it now makes it actually possible, feasible to be able to do something like that, which means that now we can actually optimize for a task and the hardware. So we can generate neural network 1 for laptop with GPU, or a microcontroller. So instead of, it's kind of a interesting big shift for neural networks, because before it was kind of you had your training data, and then it's kind of a one-shot thing to find a solution in a data center. Now we're much more looking at having this training data and generating a network that can produce all kinds of possible networks that can solve this particular problem on a particular hardware. Right? So this is kind of a very interesting change in the capabilities and the approach to generating neural network agents and modern AI systems. Now, another approach to solve this particular problem is what's called proxy tasks. Because even using hypernetworks or similar networks, inheriting weights, it still is. It's still expensive to train. So another approach would be to use a simplified but similar task for selecting the network architecture. So, for example, for ImageNet, there's like the full version of ImageNet, which has, I think, 100 classes, and then there's a small subset, CFAR10, which only has 10 classes. And instead of running and doing our search, the idea is that if a network is good at solving CFAR10, then it can solve then it can solve the full CFAR set as well. but it would be much cheaper to do it with just 10 classes as opposed to hundreds of classes. Because with the smaller set, we have smaller architectures. We also need fewer epochs usually to train it, right? We don't need to go through many. So overall, less work in number of floating point operations or parameters. So this is also a important speed up that we can do, we can achieve with our networks. Now let's have a look and see how we can apply that to our small problem here. So again, here's our current architecture. So now, how would you, what kind of changes would you propose? Or here in code like this? Well, my view would be that here we have a max pool layer, right? And what does that actually do? Max pooling in this case takes a 2 by 2. I mean, you can change the width and height of this, right? But in general, it's a 2 by 2 matrix, and it replaces this value with the maximum value in this region. So if I have 100, I have 10, 12, 115, and minus 7, then this will be 115, right? That's what max pooling does. You can see how that is a good operation to do if you're trying to do image detection, right? Because you can kind of feed certain information through the network and emphasize the important parts of it, right? The maximum parts of it. So if you want to detect if this is a chair, then all the kind of things that make up a chair should be kind of filtered through the network, right? The ones, and if it's more likely to be a dog, then those features should filter through. But if we are trying to detect if something is a square or not a square, then this kind of operation for a particular parts of the bitmap, I don't think it's very helpful, because it's kind of like blurring the image, right? If there's a red square here, now you don't know where the 115 came from. But in order to be able to figure out if something is a square or not, that kind of blurring doesn't really help, because you need to know the number of rows and you need to know the number of columns. Right? So my idea would be to get rid of the max pool layers and see if that improves it. Also, the architecture that I have here is kind of a little bit weird, because it goes from a large number of convolutional layers to a smaller number, and then it goes large again, like 64, 32, 64, 32. Usually in detection tasks, at least, you're trying to compress the data that you have to force the network into making some kind of selection. Then going up again is a bit strange. Like it's not what you would do. And sometimes you do it if you want to do auto encoder. In auto encoders, you do that where you force a network down to a small level, and then you bring it up again to the full bitmap in order to be able to generate things like images that, like GAN's generative AI, you usually do that. But for detection tasks, it would be unusual. So change the network and train it and see what the performance is. If we do something a bit more traditional, so let's say 64, 32, and also so that it trains faster. And then I don't know how many layers I have in my... At the end of this, I have a fully connected layer, or two. Only one. what did I... Oh, here I have 512 neurons. That may be a little bit high, so... But okay, just try this architecture then, 64, 32, and 512. And see what performance you get with this kind of architecture. And once you have that, then now we have a very simple network that you can train. Then see if we can reduce or change the width for our networks here. To kind of get a feeling for what happens if you change this to, let's say, 60, 64, and 68, and 28, 32, 36, and see how the accuracy changes on the task of just finding a red square. Or you can do your own task if you want to train on something else. But try and come up with a task that you can train in about 5 minutes maximum. What did I say? 60, 64, 68, and 28, or 30, 32, 34, and 128, 256, and 512 FC layers. one extra slide I wanted to do while you work on your network is one thing that I forgot to mention here. The reason why we're interested in hardware guided network architecture search, or basically finding specific network architectures that work specifically well on a particular piece of hardware, is that just taking general counters like the number of multiply accumulate operations that we need may be misleading. So for example, on a microcontroller, like the Raspberry Pi Pico that we have, for example, then if I increase the width of the hidden layer, that will greatly reduce the performance of my inference. So the latency will increase linearly or more, at least. Right? So if I have the layer and I go from 30 to 32 nodes, there is a penalty on our Raspberry Pi processors. But if I do that on a GPU, then it actually makes no difference whether I multiply. As long as I have enough VRAM, the GPU can do all of these multiplications for 30 or 32 nodes in parallel. So it doesn't really matter how many of those I have. So on a GPU, increasing or decreasing the size of the network from 64 nodes to 60 nodes most likely won't make any difference to your inference speed. As long as you have enough compute resources, enough VRAM to actually do that. The GPU can do all of that in parallel. The main bottleneck will be to take the data, the main source of latency sort of will be taking the image from the CPU and pushing it onto the GPU. Once it's on the GPU, you can run it very, very quickly. And it doesn't matter how many nodes you have there, how many neurons you have. But on a Pico, it makes a huge difference. So that's why our search has to be guided by the hardware that we're actually um, expecting to deploy it on, or the hardware that we actually want to use. So here, fix my So I modify my class so that now I have a constructor that is mm, So now I'm going to change the code here a little bit. Not sure if I have, if Python has starts with. Oh, okay. So if it starts with CNN, then we add a convolutional layer, and there will be int of x and CNN 4 colon 3 padding 1 padding else if starts with FC, then we have a starts with, oh, it's not X, in channels. And let's get rid of the max pool. I also could run the batch normalization by running the batches. Yeah, instead of one at a time, I can run batch. In channels, out channels. And then I guess I would break here because that should be the last layer. That would be the sequential layer. Here's the classifier. Okay, then I have them. Okay, and yep, that should be Ni2 now. So here's the new network, 128, 64, just so that I can modify it. 64 to 256, and then our classifier 256 goes to one output feature. Now let's have a look at this network. So train and evaluate should be the same. So here we have different flatten it, right? On the forward path. Let me add one test here. see what I missed there. Okay, let's try that. Build them up. I think the fully connected layer should just be this one, and 64. That's pretty high, eh? We'll go down to 64 and 32. Uh, $32, okay. And then that would be okay. So now that works. 16 by 16. Okay, now here we have our image, we have our training function which uses a criterion optimizer and scheduler, which should, I just want to make sure I reset the gradients in train. That's a common mistake to make, or at least for me. Yeah, okay. So we're resetting the gradients there. And another thing I want to implement, oh, I just try and train it now. come it says purchase? Yeah, always purchase. Okay, good. Anyway, that's it for today then anyway. So you can implement your own version of the network and see what variation you can get by modifying the architecture. And like I said, you can, and actually as we see from TensorFlow in the previous assignment, often you can get you can generate a network that's like 1/10 the size of the original network and still maintains the same accuracy. So there's a lot of redundancy in many trained network architectures, and optimizing it is something that we should be interested in as computer scientists.